Good evening, and welcome to Sleepy Story Facts, where a curious mind can soften and settle, and where a gentle nighttime story can carry you toward deep sleep. One quiet thought at a time. Get comfortable in whatever way feels best. Let your shoulders drop, let your jaw unclench, and allow your eyes to rest as if they've been waiting all day for permission to close. Tonight, we're drifting through nebulae, those vast clouds of gas and dust where stars are born, moving slowly, as if we're floating through cosmic nurseries, passing glowing hydrogen clouds and dark silhouettes, and lingering near places where gravity is quietly gathering material into new points of light. As you listen, you don't need to remember every detail. You can simply let the ideas pass like soft colors dissolving in water, because this is a relaxing story meant to help you fall asleep and stay asleep, with calming narration and a gentle bedtime rhythm that never asks you to hurry. Imagine the night around you as wide and quiet, and imagine the nebulae the same way, spacious, patient, and full of slow, creative motion. In the universe, nebulae are not just empty space. They are the birthplaces of stars, enormous regions where hydrogen and helium drift in thin veils, sometimes stretching for dozens or even hundreds of light years, waiting for gravity to pull them together. These clouds can seem almost invisible at first, scattered so thinly that you could pass through them and barely notice. But given enough time, small disturbances, a shock wave from a nearby supernova, the gravity of a passing star, or just the slow accumulation of mass can cause parts of the cloud to collapse inward, forming denser clumps. As those clumps grow heavier, their gravity strengthens, pulling in more gas and dust, and the center of each clump begins to heat up, compressed by the weight of everything falling toward it. Over thousands or millions of years, the temperature at the core can climb high enough to ignite nuclear fusion. And when that happens, a star is born, glowing softly at first, then brighter, casting light into the cloud that once cradled it. And yet, even as new stars ignite, the nebula around them continues to drift, still filled with material, still capable of forming more stars, as if the cloud itself is a long, gentle breath that can birth hundreds or even thousands of suns before it finally fades. Closer to the places where young stars have already formed, the nebula can begin to glow, not from its own heat, but from the radiation those stars emit. When a hot, bright star shines ultraviolet light into the surrounding hydrogen gas, that light can strip electrons from hydrogen atoms, a process called ionization. And when the electrons eventually recombine with the atoms, they release energy in the form of visible light, often a soft red glow, because that is the wavelength hydrogen prefers. These glowing regions are called emission nebulae, and they are some of the most beautiful sights in the night sky, painted in shades of crimson and pink, with wisps and tendrils curling outward like smoke frozen in time. The light they emit is gentle and steady, not harsh or blinding. And even though the nebula itself is vast and distant, the glow it produces can reach across thousands of light years, carrying a quiet message. Stars are being born here, and the process is ongoing, patient, and graceful. And as you rest here in the quiet of your own room, you can let that thought be soothing. The universe creates slowly, rushing, and even the brightest stars begin their lives in soft, glowing clouds that take their time. As we continue, imagine the same quiet night holding steady around you. You're breathing slow and unforced, while far beyond any window, nebulae keep drifting in their own unhurried way, gently shaped by starlight and gravity, the way a calm lake is shaped by a patient wind. Not all nebulae glow red like emission clouds. Some shine in different colors or don't shine at all, and the variety is part of what makes these regions so quietly fascinating. When a nebula sits near a bright star, but isn't close enough for that star's light to ionize the gas, the cloud can still reflect the starlight, scattering it the way Earth's atmosphere scatters sunlight to create a blue sky. These are called reflection nebulae, and they often appear blue or bluish-white because shorter wavelengths of light scatter more easily than longer ones, giving the nebula a soft, cool glow. Reflection nebulae are like cosmic mirrors, not creating their own light, but borrowing it from nearby stars. And they tend to look delicate and diffuse, as if the starlight has been softened by passing through a thin veil of dust. And then there are nebulae that don't glow at all, at least not in visible light. Dark nebulae are dense clouds of gas and dust so thick that they block the light from stars behind them, appearing as dark patches or silhouettes against the brighter background of the Milky Way. From our perspective, they look like holes in the sky, but they are not empty. They are full of material, cold and quiet, waiting for gravity to begin the slow work of collapsing them into new stars. Some of the most famous dark nebulae, like the Horsehead Nebula, are shaped by the way they obscure background light, their edges defined not by what they emit, but by what they hide. And there is something strangely calming about that, a presence that reveals itself only by absence, a structure that becomes visible through shadow. If you imagine holding that image lightly, it can help your mind relax nebulae as shapes in the dark, some glowing, some reflecting, some simply blocking the light beyond. All of them part of the same slow cycle of star formation and stellar evolution. Even the darkest clouds can hold the seeds of future stars, because within them, gravity is always working, pulling particles together, gathering mass into denser regions, preparing the conditions for fusion to ignite. And sometimes, when a massive star forms inside a nebula and begins to shine, its radiation can push outward, carving cavities and bubbles in the surrounding gas, creating structures that look almost sculptural, with sharp edges and hollow centers. The radiation heats the gas and drives it away, but the process is not instantaneous. It unfolds over thousands of years, and the shapes it creates, pillars, arcs, shells, can persist long after the star has finished its work, like a monument to the forces that shaped it. One of the most iconic examples is the Pillars of Creation, a region within the Eagle Nebula where dense columns of gas and dust are being slowly eroded by the ultraviolet light from nearby stars. The pillars themselves are several light years tall, towering structures that look almost solid in images, but they are made of material so thin that if you were inside one, you might not even notice it around you. At the tips and edges of the pillars, gravity is still at work, forming small knots of gas that may one day become stars themselves. And in that way, the pillars are both being destroyed and giving birth at the same time, eroded by starlight, yet still capable of creating new light. It is a gentle kind of paradox. The idea that creation and destruction can happen together, not as opposites, but as parts of the same slow transformation. And it fits with the way nebulae exist in general, always changing, always drifting, never fixed, but never in a hurry. And as you listen, you can let your mind do what nebulae do, move gently through time, without holding on to any particular shape, just flowing from one soft idea to the next, always becoming, never needing to stay perfectly still. Stay exactly where you are in this calm moment of night, and let your mind drift a little deeper into the quiet beauty of nebulae. Because even within these vast clouds, there are smaller details that reveal how delicate and patient the universe can be. When young stars begin to shine inside a nebula, they don't just light up the gas around them, they also shape it, pushing and pulling at the material with radiation pressure and stellar winds, creating structures that can look almost like sculptures carved from light and dust. These young stars are often very hot and very bright, burning with the intense energy of youth, and their ultraviolet radiation can heat the surrounding gas to thousands of degrees, causing it to expand outward and creating what astronomers call an HII region, named after ionized hydrogen. HII regions are the glowing hearts of Emission nebulae, places where the gas is so energized by starlight that it radiates its own light in return. And they can be enormous, sometimes dozens of light years across, filled with swirling clouds and bright filaments that trace the paths where gas is moving, colliding, or being compressed. The shapes within these regions are not random. They are guided by the interplay of gravity, pressure, and radiation. And the result is often a kind of cosmic architecture, with walls, caverns, and arches formed from nothing more than gas and light. And within these glowing regions, new stars continue to form, because even as radiation pushes gas away, it can also compress nearby material, triggering fresh collapses and creating a feedback loop where one generation of stars helps create the next. In this way, star formation can spread through a nebula like a slow wave, not all at once, but in clusters and groups, each one stirring the gas around it and preparing the conditions for more stars to ignite. Some nebulae are particularly efficient at this process, forming hundreds or even thousands of stars in a relatively short time, at least by cosmic standards. And when that happens, the region can become what is known as a stellar nursery, a place where stars are born in abundance, clustered together in groups that will eventually drift apart over millions of years, but for now remain gravitationally bound, sharing the same birthplace and the same early history. The Orion Nebula is one of the closest and most studied stellar nurseries, visible even to the naked eye as a faint smudge in the Sword of Orion. And within it, astronomers have found hundreds of young stars, many of them surrounded by disks of gas and dust that may one day form planets, just as the disk around our own sun formed Earth and the other worlds of the solar system. It is a comforting thought, the idea that nebulae are not just birthplaces for stars, but also for planetary systems, places where the raw material of the universe is gathered and shaped into worlds that might one day host life. And even if most of those worlds remain cold and lifeless, the possibility is always there, a quiet potential woven into the fabric of every nebula. And sometimes, the material in a nebula is not evenly distributed. Instead, it can clump into dense knots and filaments, guided by magnetic fields and turbulence, creating structures that look almost biological, like veins or roots spreading through the cloud. These filaments can be incredibly long, stretching for light years, and they often serve as channels where gas can flow and gather, feeding the formation of new stars along their length. In a way, the filaments are like cosmic highways, guiding matter from one region to another, and the stars that form along them can sometimes appear in chains or lines, as if they are following a hidden path through the nebula. And as you rest here in the quiet of your own room, you can let that image be soothing. The universe has structure even in its chaos, and even the most diffuse clouds of gas have a kind of order, a pattern that emerges from the simple forces of gravity and pressure, creating beauty without effort, without needing to rush. Let yourself remain settled in the same gentle night, as if the room around you has become a quiet observatory, and your thoughts are simply drifting slowly, kindly past one nebula after another. A comforting thing about these cosmic clouds is that they exist on timescales so vast that change feels almost like stillness. And even the most violent processes star birth, shock waves, radiation carving through gas unfold so slowly from a human perspective that they seem gentle, patient, as if the universe has all the time it needs and never needs to hurry. Within nebulae, the gas is not just hydrogen. It also contains helium, the second most abundant element, along with traces of heavier elements like carbon, nitrogen, and oxygen, all of them mixed together in a thin soup that fills the space between stars. These heavier elements were not present when the universe first formed. They were created inside earlier generations of stars, forged in the heat of nuclear fusion, and then scattered into space when those stars died, either through quiet winds or violent explosions. In that way, every nebula carries a kind of memory, a chemical signature of the stars that came before, and the new stars that form from that material inherit those elements, incorporating them into their own structure. And if they form planets, into the worlds that orbit them, it is a gentle kind of recycling. The idea that the atoms in your own body, carbon, oxygen, nitrogen, were once inside a star, and before that were part of a nebula, drifting through space, waiting to be gathered into something new. And the process is ongoing. Even now, stars are dying and enriching the interstellar medium with new material, and nebulae are forming from that material, and new stars are being born, continuing the cycle that has been unfolding for billions of years. Some nebulae are the direct remnants of dying stars, formed when a star at the end of its life expels its outer layers into space, creating a glowing shell of gas that expands outward over thousands of years. These are called planetary nebulae, not because they have anything to do with planets, but because early astronomers thought they looked round and planet-like through their telescopes, and the name stuck. planetary nebulae are often strikingly beautiful, with intricate shapes and vivid colors, because the gas in them is ionized by the hot core of the dying star, which remains at the center as a white dwarf, still shining brightly even as it slowly cools over billions of years. The shapes of planetary nebulae can be complex spheres, rings, butterflies, hourglasses, and those shapes are determined by factors like the star's rotation, magnetic fields, and whether it had a companion star that influenced how the gas was expelled. And within those shapes, the gas is moving, expanding at speeds of tens of kilometers per second, fast by everyday standards, but slow enough that the nebula can remain visible for thousands of years before it finally disperses into the interstellar medium and becomes indistinguishable from the background gas. Another kind of nebula forms not from a gentle expulsion, but from a violent explosion. When a massive star reaches the end of its life and runs out of fuel, its core collapses in a fraction of a second, releasing an enormous amount of energy that blows the star apart in a supernova. One of the most energetic events in the universe, the explosion sends a shock wave racing outward through the surrounding space at thousands of kilometers per second, sweeping up gas and dust and compressing it into a glowing shell. These supernova remnants can be vast, expanding for tens of thousands of years and growing to hundreds of light years across. And they are often some of the most complex and beautiful nebulae we can observe, filled with filaments, knots, and regions where the shock wave has compressed the gas into dense clumps that glow in different colors depending on which elements are present. The Crab Nebula is one of the most famous supernova remnants, formed by a supernova that was observed by astronomers in the year 1054. And even today, nearly 1,000 years later, the nebula is still expanding, still glowing, powered by a rapidly spinning neutron star at its center that pulses with energy and drives winds of charged particles through the surrounding gas. And as you rest here, you can let these facts move past like soft scenery. Emission, nebulae glowing red; reflection, nebulae shining blue; dark nebulae blocking the light; HII regions carved by starlight; stellar nurseries filled with young stars; planetary nebulae expelled by dying stars; and supernova remnants expanding from ancient explosions, each one part of the same long, quiet story. And if you're getting sleepy, that's perfect too, because this nighttime story is not asking you to hold on. It's inviting you to drift, to loosen your thoughts, and to let the universe feel far away and gentle while your body stays safe and still, here in the dark, on its way toward deep sleep. Let the night keep holding you the way it is now, quiet, steady, and unhurried, while your breathing continues at its own gentle pace. And while, far beyond our little corner of Earth, nebulae keep doing what they have always done, drifting, gathering, and changing so slowly that the change feels more like a soft whisper than an event. In the last part, we lingered with supernova remnants and planetary nebulae. And now we can shift our attention to the way nebulae interact with the light and radiation around them. Because even though these clouds are mostly empty space, they have a remarkable ability to shape and scatter light, creating some of the most visually stunning objects in the night sky. When starlight passes through a nebula, the dust particles in the cloud can scatter that light in different directions. And because shorter wavelengths of light scatter more efficiently than longer ones, the scattered light often appears blue. The same reason Earth's sky is blue during the day. Reflection nebulae are not just passive clouds. They are active participants in the way we see the universe, taking the light from nearby stars and redistributing it, softening it, and giving it a cool, ethereal glow that can make the nebula look almost ghostly in photographs. And because the dust particles themselves are tiny, often smaller than a micron, about the size of the particles in smoke, they are incredibly effective at scattering light. And even a thin veil of dust can create a noticeable effect, turning a faint star into a glowing patch of light that spreads across the sky. Some reflection nebulae are found near bright stars that are not hot enough to ionize the surrounding gas. So instead of glowing red like an emission nebula, the cloud simply reflects the starlight, creating a soft blue haze that surrounds the star like a gentle aura. The Pleiades star cluster, also known as the Seven Sisters, is one of the most famous examples of this. The cluster is surrounded by a reflection nebula that is visible in long exposure photographs, even though it is faint and difficult to see with the naked eye. The stars in the Pleiades are young, hot, and blue, and the nebula around them reflects that blue light, creating a scene that looks almost like stars wrapped in silk, delicate and luminous. And in some cases, nebulae can combine both emission and reflection, with part of the cloud ionized and glowing red, while another part reflects blue light, creating a multicolored scene that shifts from one hue to another depending on where you look. These mixed nebulae are reminders that the universe does not always fit into neat categories. Instead, it blends and overlaps, creating gradients and transitions that are softer and more subtle than we might expect. And even though nebulae are often described as clouds, they are not dense by any ordinary measure. The gas and dust are spread so thinly that even the thickest nebulae are better vacuums than anything we can create in a laboratory on Earth. And yet, over distances of light years, that thin material adds up, and the cumulative effect is enough to block starlight, scatter radiation, and give birth to new stars. It is a gentle reminder that in the universe, scale matters, and what seems negligible on a small level can become profound when stretched across enormous distances and vast spans of time. And within nebulae, the temperature can vary widely depending on where you are. In the dense cores where stars are forming, the gas can be compressed and heated to thousands of degrees, while in the outer regions, far from any stars, the temperature can drop to just a few degrees above absolute zero, so cold that atoms move slowly and molecules can form and survive for long periods. These cold regions are often where the densest clumps of gas are found, because the low temperature means the gas cannot resist gravity's pull as effectively, and it is easier for material to collapse and begin the process of forming a star. Astronomers often study these cold, dense regions using radio telescopes, which can detect the faint emissions from molecules like carbon monoxide and formaldehyde, allowing them to map the distribution of gas and identify places where star formation is likely to occur. And in a way, those radio emissions are like the quiet heartbeat of the nebula, a signal that reveals where the action is happening, even when visible light cannot penetrate the dust. And sometimes, when a hot young star forms inside a dense cloud, its radiation can begin to clear out the surrounding material, creating a bubble or cavity in the nebula. The radiation heats the gas and drives it away. And over time, the cavity can grow to several light years across, leaving the star at the center of a hollow region with walls made of compressed gas and dust. These cavities are often where we see the most dramatic structures, because the edges of the cavity are where the radiation is actively interacting with the nebula, ionizing the gas and causing it to glow. And the shapes that result, shells, filaments, arcs, can be incredibly intricate, as if the star is sculpting the nebula from the inside out. And within those walls, gravity is still at work, pulling material together. And sometimes, new stars can form in the compressed gas at the edges of the cavity, triggered by the very radiation that created the cavity in the first place. In this relaxing nighttime story, the theme is gentle transformation. Nebulae scattering light, reflecting starlight, glowing in red and blue, forming stars in cold, dense cores, and being shaped by the radiation from the stars they create. And if your thoughts are starting to loosen, that's perfect, because you don't need to stay fully awake to let wonder wash over you. Settle back into the same quiet night and let the thoughts that are still awake in you slow down, the way a lake smooths out after a breeze has passed. Because this is still a gentle bedtime story, a relaxing sleep story meant to help you fall asleep and stay asleep as we drift from one calm nebula fact to the next. Out in the universe, some nebulae are so vast that even light, traveling at 300,000 kilometers per second, takes years to cross them from one side to the other. And even though that sounds enormous, you can hold it lightly, just as a soft reminder that space can be wide, and that distance can be peaceful when you don't have to cross it. And while the largest nebulae stretch for hundreds of light years closer in, many nebulae are more modest in size, filling regions that are still immense by human standards, but small enough that we can begin to study them in detail, mapping the distribution of gas and dust, identifying individual stars, and watching how the nebula changes over time. Some of the most interesting nebulae are those where multiple generations of star formation are happening at once, with older stars already shining brightly, while new stars are still forming in the denser regions nearby. And the interaction between these generations can create feedback loops where the radiation and winds from older stars influence the formation of younger ones, either triggering new collapses or disrupting them, depending on the circumstances. And there are nebulae that seem to hide their brightest work behind curtains. In some systems, thick dust clouds absorb visible starlight, making them faint or almost invisible to ordinary optical telescopes, even while inside those dusty regions stars may be forming actively, warming the dust and causing it to glow in infrared and submillimeter light. These dust-rich nebulae remind us that the universe has layers. What looks dark in one kind of light can be bright in another, and what appears quiet can hold busy star birth behind a veil. infrared telescopes have revolutionized our understanding of these hidden regions, allowing us to see through the dust and discover protostars, young stars that are still gathering mass from their surroundings and have not yet ignited fusion in their cores. Protostars are often surrounded by thick disks of gas and dust, and those disks are where planets may eventually form. So studying them gives us insight into how solar systems like our own came to be. And within these disks, the material is not static. It is moving, spiraling inward toward the protostar, driven by gravity and friction. And as it moves, it can heat up and release energy, making the disk glow even before the star itself begins to shine. Sometimes, protostars also launch jets, narrow streams of gas that shoot out from the poles of the star at high speeds, driven by magnetic fields and the rotation of the disk. These jets can extend for light years, punching through the surrounding nebula and creating bright knots and shock waves where they collide with the ambient gas. The jets are a sign that the protostar is actively accreting material, and they can help regulate the star's growth by carrying away excess angular momentum, allowing more material to fall onto the star without causing it to spin too fast. And when these jets collide with the nebula, they can compress the gas and trigger new episodes of star formation, creating a ripple effect where one protostar helps create others nearby. In the dense environments of stellar nurseries, star formation is rarely an isolated event. Instead, it happens in clusters, with dozens or hundreds of stars forming in the same region over a relatively short period of time. These clusters are often embedded in the nebula at first, hidden by the gas and dust that gave birth to them. But over time, the radiation and winds from the young stars clear away the surrounding material, and the cluster emerges, shining brightly and illuminating the remnants of the nebula that once surrounded it. Some clusters remain gravitationally bound and drift through space together for millions of years, while others are more loosely connected and eventually disperse, their stars spreading out and becoming part of the general stellar population of the galaxy. And within these clusters, the stars are often very young, just a few million years old, and they are still surrounded by the disks and envelopes of material from which they formed, making them ideal targets for studying the early stages of stellar evolution and planet formation. Observations of these young clusters have revealed that many stars are born with planets already forming around them, and that the process of planet formation begins very early, even before the star itself has fully settled onto the main sequence. And if you're still awake, you can let these facts move past like soft scenery infrared, revealing hidden protostars, disks surrounding young stars, jets launching from poles, star clusters forming in groups, and planets beginning to take shape even before their stars have fully ignited. And if you're getting sleepy, that's perfect too, because this nighttime story is not asking you to hold on. It's inviting you to drift, to loosen your thoughts, and to let the universe feel far away and gentle, while your body stays safe and still, here in the dark, on its way toward deep sleep, somewhere beyond the quiet room you're in right now. Nebulae are still drifting in their slow, patient ways, and you don't have to follow them with effort. You can just let the ideas pass through your mind like soft, distant light. In the last part, we talked about protostars and jets, and now we can widen our view again to the way nebulae contribute to the larger ecosystem of the galaxy. Because even though nebulae are birthplaces for stars, they are also part of a continuous cycle, a flow of material that moves from stars back into space and then into new stars over and over again. For as long as the galaxy exists, when stars like the sun reach the end of their lives, they do not explode. Instead, they expand into red giants, shedding their outer layers gently over thousands of years, creating planetary nebulae that drift outward and eventually mix with the interstellar medium. And when massive stars explode as supernovae, they inject enormous amounts of energy and material into the surrounding space, creating shock waves that can travel for tens of thousands of years, sweeping up gas and dust and compressing it into new structures. In both cases, the material that returns to space is enriched with heavier elements, and those elements become part of the next generation of nebulae, which means the next generation of stars and the next generation of planets. It is a cycle that has been ongoing for billions of years, and it is the reason why planets like Earth exist at all. Because the atoms that make up our world were forged inside stars that lived and died long before the sun was born. And within the Milky Way, this cycle is happening constantly, with nebulae forming, stars being born, stars dying, and new nebulae emerging from the remnants. All of it unfolding at different rates in different regions of the galaxy. In the spiral arms, where gas is denser and star formation is more active, nebulae are common and often filled with young, hot stars that light up the surrounding gas with their radiation. In the central bulge of the galaxy, where the stars are older and the gas is thinner, nebulae are less common, and star formation has slowed to a quieter pace. And in the halo, far from the disk, the gas is so diffuse that nebulae are rare, and most of the stars are ancient, formed in the early days of the galaxy's history, and still drifting through space on slow, elliptical orbits. Each region of the galaxy has its own rhythm, its own balance between star formation and stellar death, and nebulae are the markers of where that balance is most active, the places where the cycle is turning most visibly. Some nebulae are associated with specific regions of active star formation, known as OB associations, named after the hot, massive O and B type stars that dominate them. These stars are among the brightest and shortest lived in the galaxy, burning through their fuel in just a few million years and ending their lives in spectacular supernova explosions. Because they are so massive and so bright, they have a profound influence on their surroundings, ionizing vast regions of gas, driving powerful winds, and triggering new waves of star formation through their radiation and eventual explosions. OB associations are often found in the spiral arms of the galaxy, where the density of gas is high and the conditions for forming massive stars are favorable. And within these associations, the nebulae are among the largest and most luminous in the galaxy, glowing brightly in red and blue, filled with intricate structures, and often home to dozens or even hundreds of young stars. And as you rest, you can hold this one quiet image, a nebula as part of a cycle, not just a static cloud, but a living part of the galaxy's metabolism, a place where material gathers, stars form, and eventually the material is returned to space, ready to begin the cycle again. And if your mind feels like it's drifting now, that's exactly right, because these are not facts you need to grip. They're facts you can let float, while your breathing stays soft and your body sinks a little deeper into rest. Let yourself stay comfortable where you are, and let the universe keep doing its slow work far away, because tonight you don't have to chase any of these ideas. You can simply listen and let the facts arrive like gentle footsteps across a quiet room, one after another, fading softly as soon as they pass. In the last part, we lingered with the cycle of material in the galaxy. And now, we can turn our attention to some of the most famous and most studied nebulae, the ones that have become icons in astronomy and in our understanding of how stars form. The Orion Nebula, also known as Messier 42 or M42, is one of the closest and brightest nebulae visible from Earth. Located about 1,350 light-years away in the constellation Orion, it is visible to the naked eye as a fuzzy patch in the middle of Orion's sword. And through a telescope, it reveals an intricate structure of glowing gas and dark dust lanes, with a cluster of hot young stars at its heart, known as the trapezium. The trapezium stars are responsible for ionizing much of the gas in the nebula, causing it to glow in shades of red and pink. And their intense radiation is also carving cavities in the surrounding cloud, creating a dynamic and ever-changing landscape. The Orion Nebula is a stellar nursery, home to hundreds of protostars and young stars, many of them surrounded by protoplanetary disks that may one day form planets. Observations of these disks have provided some of the best evidence we have for how solar systems form, and the nebula has become a laboratory for studying the early stages of stellar and planetary evolution. And because it is so close and so bright, the Orion Nebula has been studied extensively at every wavelength, from radio to X-rays, revealing layers of structure and complexity that are not visible in optical light alone. Another famous nebula is the Eagle Nebula, also known as Messier 16 or M16. Located about 65 light-years away in the constellation Serpens, the Eagle Nebula is best known for the pillars of creation, 3 towering columns of gas and dust that have become one of the most iconic images in astronomy, captured by the Hubble Space Telescope in 1995 and again in higher resolution in 2014. The pillars are part of a larger region of active star formation, and they are being slowly eroded by the ultraviolet radiation from nearby hot stars, which is sculpting them into their distinctive shapes. At the tips and edges of the pillars, dense knots of gas are collapsing under gravity, forming new protostars that are still hidden inside the dusty cocoons. The pillars themselves are enormous, several light-years tall, but they are also fragile, and astronomers estimate that they may be destroyed completely within a few million years as the radiation continues to chip away at them. And yet, even as they are being eroded, are still capable of forming new stars, creating a poignant image of creation and destruction happening simultaneously. The Carina Nebula, located about 75 light-years away in the southern constellation Carina, is one of the largest and brightest nebulae in the Milky Way, spanning over 300 light-years across, and home to some of the most massive stars known, including Eta Carinae, a giant star that is nearing the end of its life and may explode as a supernova at any time. The nebula is filled with glowing gas, dark dust lanes, and towering pillars similar to those in the Eagle Nebula, and it is a site of intense star formation, with thousands of young stars scattered throughout the region. The radiation from these stars illuminates the nebula in shades of red, orange, and blue, creating a scene that looks almost like a cosmic landscape, with mountains and valleys carved from gas and dust. The Carina Nebula has been the subject of numerous studies, and recent observations by the James Webb Space Telescope have revealed even more detail, uncovering previously hidden protostars and showing the intricate structure of the dust and gas in unprecedented clarity. And as you rest, you can let these images drift past the Orion Nebula glowing in Orion's sword, the pillars of creation towering in the Eagle Nebula, the vast expanse of the Carina Nebula filled with massive stars each. One, a reminder that nebulae are not just abstract clouds of gas, but real places in the universe, filled with structure, motion, and the ongoing process of star formation. And if your thoughts are starting to blur at the edges, that's perfect, because the universe is still there, whether you hold it sharply or let it soften into sleep. Stay with the quiet pace you found now, and let your breathing remain easy and natural, because this part of our sleep story is about something gentle and reassuring: how nebulae reveal themselves through different kinds of light, and how each wavelength tells a different part of the story. We've been drifting through famous nebulae and stellar nurseries, and now we can soften our attention even more and simply look without effort into the layers of light that nebulae emit and reflect. Invisible light. Nebulae can appear as glowing clouds, their colors determined by which gases are present and how they are being ionized. Red light often comes from hydrogen, the most abundant element in the universe, while green and blue-green light can come from oxygen, especially doubly ionized oxygen, which emits a characteristic line in the green part of the spectrum. These colors blend together in complex ways, creating nebulae that can appear pink, purple, or even multicolored, depending on the mix of gases and the intensity of the radiation from nearby stars. But visible light is only a small part of the electromagnetic spectrum, and nebulae shine at many other wavelengths that our eyes cannot see. In the infrared, for example, nebulae often appear much brighter and more extensive than they do in visible light, because infrared light can penetrate dust that blocks visible wavelengths, revealing the warm glow of dust heated by young stars. Infrared observations have uncovered entire populations of protostars that were previously hidden, and they have shown that many nebulae are far more active than they appear in optical images. The James Webb Space Telescope, which observes primarily in the infrared, has been particularly effective at peering through dusty nebulae, and revealing the stars forming inside, often showing dozens or even hundreds of protostars in regions that looked nearly empty in visible light. And in the far infrared and submillimeter wavelengths, astronomers can detect the cold dust that pervades nebulae, tracing the densest regions where stars are most likely to form, and mapping the large-scale structure of the cloud at the other end of the spectrum in the ultraviolet and X-ray wavelengths. Nebulae can reveal the hottest and most energetic processes at work. Ultraviolet light is absorbed by dust and gas, so it doesn't travel far through a nebula, but it is the primary driver of ionization. And young, hot stars emit most of their energy in the ultraviolet, even though that light is not visible to our eyes. X-rays, on the other hand, can be produced by very hot gas, especially in regions where shock waves from supernova remnants or stellar winds are colliding with the surrounding material, heating it to millions of degrees. Observations of nebulae in X-rays often reveal the presence of young stars with intense magnetic activity, as well as the remnants of previous generations of stars that exploded as supernovae and left behind hot, expanding shells of gas. And in the radio part of the spectrum, nebulae emit faint signals from molecules and ionized gas, allowing astronomers to study the kinematics of the cloud, how the gas is moving, where it is dense, and where it is being compressed by gravity or radiation. Radio observations have been particularly important for mapping the distribution of cold, dense gas in nebulae, because radio waves can pass through dust unimpeded, and they can detect molecular lines from species like carbon monoxide, which traces the coldest and densest regions where stars are forming. In this way, each wavelength of light adds a layer to our understanding, like different instruments in an orchestra playing together to create a full picture of what is happening inside the nebula. And the beauty of this multi-wavelength approach is that it reveals complexity without needing to explain everything at once. You can hold the idea lightly that nebulae are not simple objects, but layered environments, and each layer tells a different story, and together they form a richer, more complete understanding of how stars are born. And as you rest, you can let this thought be soothing. The universe is revealing itself constantly in many different kinds of light, and even though we cannot see most of those wavelengths with our eyes, we have built instruments that can, and through them, we can glimpse the hidden beauty of nebulae in all their complexity. Let your mind stay soft and unhurried as we move into another calm set of nebula facts, the kind that feel almost like watching slow patterns in water motion, balance, and shape, all guided by gravity. In the last part, we drifted through different wavelengths of light, and now we can come a little closer again, back to the physical processes happening inside nebulae, because even though these clouds are vast and diffuse, they are also governed by forces that are surprisingly simple: gravity, pressure, magnetism, and radiation. Gravity is the primary force that drives star formation, pulling gas and dust together into denser and denser clumps until the center becomes hot enough to ignite fusion. But gravity does not work alone. It is always opposed by pressure, which resists compression and tries to push the gas outward. In a stable cloud, gravity and pressure are balanced, and the cloud can remain in equilibrium for a long time, neither collapsing nor dispersing. But if something disturbs that balance, a shock wave from a nearby supernova, the gravitational influence of a passing star, or even just a random fluctuation in density, then gravity can begin to win, and parts of the cloud can start to collapse. The collapse is not instantaneous. It happens over thousands or millions of years, and as the cloud shrinks, its gravity grows stronger, pulling in more material and accelerating the process. Eventually, the center of the collapsing cloud becomes so dense and so hot that hydrogen nuclei begin to fuse into helium, releasing energy and halting the collapse, and a star is born. But the process is messy and complex, and not every collapsing cloud becomes a single star. Often, the cloud fragments into multiple pieces, each one forming its own star, and the result is a binary system, or a cluster of stars, all born from the same initial cloud. And within these forming systems, the gas and dust that do not fall onto the stars can settle into disks, where planets may eventually form, creating entire solar systems from the remnants of the nebula. Magnetism also plays a role, though it is less obvious than gravity. Nebulae contain weak magnetic fields that thread through the gas, and these fields can influence how the gas moves and collapses. In some cases, magnetic fields can slow down the collapse by providing additional support, resisting gravity in a way that is different from pressure. And when a protostar forms and begins to rotate, the magnetic field can become twisted and amplified, channeling gas into narrow jets that shoot out from the poles of the star, carrying away angular momentum and allowing more material to fall onto the star. These jets are one of the most striking features of star formation, visible as long, narrow streams of glowing gas that extend for light years into the surrounding nebula. And they are a direct consequence of the interplay between rotation, magnetism, and gravity. Radiation, too, shapes the nebula in profound ways. As soon as a star begins to shine, its light pushes outward on the surrounding gas and dust, exerting a force called radiation pressure. For small dust particles, radiation pressure can be strong enough to push them away from the star, clearing out a region around it and creating a cavity. And when multiple stars form in a cluster, their combined radiation can carve out large bubbles in the nebula, compressing the gas at the edges and potentially triggering new episodes of star formation. The radiation also ionizes the gas, stripping electrons from atoms and causing the nebula to glow in visible light. And the color and brightness of that glow depend on how much radiation is present and which gases are being ionized. And sometimes, radiation can have the opposite effect, not triggering star formation, but preventing it by heating the gas so much that it cannot collapse under gravity. In this way, star formation is a self-regulating process where the stars that form influence weather and where new stars can form nearby, creating feedback loops that determine the overall efficiency and rate of star formation in the nebula. And as you rest here, you can let that be a soothing thought. Even the most complex processes in the universe are built from simple forces: gravity pulling, pressure resisting, magnetism guiding, radiation shaping and the interplay of those forces creates the structures we see, the nebulae and stars and planets, all of it emerging naturally from the laws of physics without needing to be controlled or directed. Let your breathing continue its steady rhythm as we turn toward another set of nebula facts, this time focusing on the timescales involved in star formation and how, even though the process feels slow from a human perspective, it is actually quite rapid on cosmic terms. Nebulae can exist for millions of years, drifting through the galaxy, slowly changing shape as they are stirred by turbulence and compressed by passing shock waves. But once a region within the nebula begins to collapse under gravity, the process accelerates dramatically, and a star can form in just a few 100,000 years, a blink of an eye compared to the age of the galaxy. The earliest stage of star formation is called the prestellar phase, when a dense core has formed within the nebula, but has not yet begun to collapse. These cores are cold, just a few degrees above absolute zero, and they are held in place by a delicate balance between gravity and the internal pressure of the gas. They can remain in this state for a long time, perhaps millions of years. But eventually, something triggers the collapse shock wave, a gravitational perturbation, or simply the slow accumulation of more mass, and the core begins to contract. As it contracts, it heats up, and the material falls inward faster and faster, drawn by the growing gravity of the forming protostar at the center. Within a few tens of thousands of years, the protostar has gathered enough mass that it begins to shine, not yet from fusion, but from the heat generated by the infalling material. And this marks the beginning of the protostellar phase. During this phase, which can last for hundreds of thousands of years, the protostar continues to accrete mass from the surrounding disk and envelope, growing larger and hotter, and eventually the temperature at its core reaches about 10 million degrees, hot enough for hydrogen fusion to begin. When fusion starts, the protostar becomes a true star, shining with its own energy, and it enters the main sequence, the long, stable phase of stellar life, where it will spend most of its existence. For a star like the Sun, the main sequence lasts about 10 billion years, far longer than the few 100,000 years it took to form, which means that star formation is a relatively brief episode in a star's life, a rapid transition from cloud to shining object. But during those few 100,000 years, the nebula around the forming star changes dramatically, carved and sculpted by the star's radiation and winds. And by the time the star reaches the main sequence, much of the nebula may have been dispersed or blown away, leaving the star exposed and visible. Some nebulae, especially those forming massive stars, can be transformed even more rapidly. Massive stars form faster than low-mass stars, sometimes in just a few tens of thousands of years, because their gravity is stronger, and they can pull in material more quickly. But they also have a much greater impact on their surroundings, because they are hotter and brighter, and produce much more radiation. A massive star can ionize and heat the gas around it so effectively that it creates an expanding bubble of hot, ionized gas that can grow to tens of light years across in just a few million years. These bubbles are often visible as bright HII regions, and they can trigger new star formation at their edges, where the expanding shell compresses the surrounding gas and causes it to collapse. In this way, massive stars can create waves of star formation that spread through the nebula, with each generation of stars triggering the next, until the nebula is exhausted and no more stars can form. And sometimes, when a massive star reaches the end of its life and explodes as a supernova, the explosion can inject so much energy into the nebula that it disrupts star formation entirely, blowing the remaining gas away and leaving behind only the stars that have already formed. This feedback from massive stars is one of the main reasons why star formation in nebulae is not perfectly efficient. Only a small fraction of the gas in a nebula actually ends up in stars, with the rest being dispersed back into the interstellar medium. And as you rest, you can let this be a calming thought. The universe creates on many different timescales, from the rapid formation of stars in a few 100,000 years to the slow drift of nebulae over millions of years, to the long, stable lifetimes of stars on the main sequence that last for billions of years. And all of these timescales are part of the same continuous process, the cycle of matter moving from diffuse clouds to dense stars and back again. Let's keep moving gently forward into some of the smaller details that make nebulae so endlessly fascinating to study. Because not every nebula is a giant cloud spanning hundreds of light years. Some are much smaller and more localized, formed around individual stars or small groups of stars. And these smaller nebulae can be just as interesting and just as important for understanding how stars and planets form. One type of small nebula is the cometary globule, a dense, compact cloud of gas and dust that has been shaped by the radiation from nearby hot stars into a teardrop or comet-like shape, with a dense head and a long tail streaming away from the source of radiation. Cometary globules are often found on the edges of larger HII regions, where the intense radiation from massive stars is eroding the surrounding cloud, and they can be sites of low-mass star formation, protected from the full force of the radiation by their dense cores. The tails of cometary globules can stretch for light years, pointing away from the ionizing stars like cosmic windsocks, and they are a visible reminder of the way radiation pressure can sculpt and shape the interstellar medium. Another type of small nebula is the Bok globule, a dark, dense cloud of gas and dust that appears as a black silhouette against a brighter background. Bok globules are named after the astronomer Bart Bok, who studied them extensively in the mid-20th century, and they are often the sites of low-mass star formation, containing enough material to form one or a few stars. They are typically just a few light years across, and their densities can be much higher than the surrounding nebula, making them ideal places for gravity to overcome pressure and trigger collapse. Observations of Bok globules have revealed that many of them contain protostars, or young stars, hidden inside, invisible in optical light, but detectable in the infrared, where the warm dust surrounding the forming star glows brightly. And because Bok globules are relatively isolated, they provide a simpler environment for studying star formation than the more complex and crowded regions of larger stellar nurseries. And then there are the reflection nebulae we mentioned earlier, which are often small and localized, formed around single stars or small clusters. These nebulae do not glow from internal ionization, but simply reflect the light of nearby stars, and their appearance can change depending on the angle from which they are viewed and the distribution of dust within them. Some reflection nebulae are associated with young stars that are still partially embedded in their birth clouds, and the dust around them can scatter the starlight in intricate patterns, creating scenes that look almost three-dimensional, with layers and veils of light shifting as you change perspective. And within these nebulae, the dust is not just passive. It is also interacting with the starlight, absorbing energy and re-emitting it at longer wavelengths, warming slightly and contributing to the infrared glow that surrounds many young stars. And in some cases, the dust can even play a role in the chemistry of the nebula, providing surfaces where molecules can form and react, creating complex organic compounds that may one day become part of planets and possibly life. The idea that nebulae are not just birthplaces for stars, but also for the chemical building blocks of life is a comforting and profound one, linking the distant clouds of gas and dust to the very origin of everything we know. And as you rest, you can hold this image lightly. A small, dark globule drifting through space, cold and quiet. But inside it, gravity is working, pulling material together. And soon within a few 100,000 years, a star will ignite, and the darkness will give way to light. Let your thoughts drift into a softer kind of seeing now, because we've been exploring nebulae from many angles. And now we can turn our attention to the way these clouds fit into the larger structure of the galaxy. Nebulae are not randomly scattered through space. They are concentrated in certain regions, especially the spiral arms of the Milky Way, where the density of gas is higher, and the conditions for star formation are most favorable. The spiral arms are not fixed structures, but density waves, regions where gas and stars are compressed as they move through the galaxy. And that compression triggers star formation, creating bright HII regions and stellar nurseries that trace out the spiral pattern. From above, the Milky Way would appear as a beautiful spiral, with bright arms glowing in red and blue from the nebulae and young stars that populate them, and darker lanes between the arms where the gas is thinner and star formation is less active. And within those spiral arms, nebulae come in all sizes and shapes, from the giant molecular clouds that can span hundreds of light years and contain enough material to form millions of stars, to the small Bach globules that might produce only one or two. The largest nebulae are often referred to as giant molecular clouds, or GMCS, and they are the most massive structures in the interstellar medium, with masses ranging from tens of thousands to millions of times the mass of the Sun. These clouds are called molecular because the gas within them is cold enough and dense enough that hydrogen atoms can pair up to form hydrogen molecules, which are more stable and harder to disrupt than individual atoms. GMCS are the primary sites of star formation in the galaxy, and they can contain dozens or even hundreds of smaller regions where stars are actively forming, each one corresponding to a dense core or cluster of cores within the larger cloud. And because they are so massive and so extended, GMCS have their own internal structure, with filaments, clumps, and cores distributed throughout, connected by a network of lower density gas that fills the spaces between. The structure of a GMC is shaped by turbulence, magnetic fields, and gravity, and it is constantly evolving as parts of the cloud collapse to form stars, while other parts are dispersed by the radiation and winds from those stars. Over time, a GMC can form thousands of stars, organized into clusters and associations, and eventually, the feedback from those stars can disrupt the cloud entirely, dispersing the remaining gas and leaving behind only the stars themselves, which will continue to drift through the galaxy long after the nebula that formed them has disappeared. And in the spaces between the spiral arms, where the density of gas is lower, nebulae are less common, but they are not entirely absent. There are diffuse clouds of gas and dust that fill the interstellar medium, too thin to form stars on their own, but still capable of scattering starlight and contributing to the overall glow of the galaxy. These diffuse clouds can sometimes be compressed by passing shock waves or by the gravitational influence of the spiral arms. And when that happens, they can collapse and form new stars, even in regions that were previously quiet. In this way, the galaxy is a dynamic environment, with gas and dust constantly moving, being compressed and dispersed, forming stars, and being replenished by the death of stars. All of it happening on timescales that range from thousands to billions of years. And as you rest, you can picture the Milky Way as a vast, slowly turning spiral, with nebulae scattered along its arms like glowing jewels, each one a site of creation, a place where the raw material of the universe is being transformed into stars and planets, and perhaps life. Keep your breath slow as we drift into the idea that nebulae, for all their beauty and complexity, are also temporary structures, destined to be dispersed over time by the very stars they create. When a nebula begins to form stars, those stars do not sit passively within the cloud. They immediately begin to affect their surroundings, emitting radiation and winds that push outward against the gas. For low-mass stars like the Sun, this feedback is relatively gentle, and it may take millions of years for the star to clear out the material around it. But for massive stars, the feedback is much more intense, and it can disrupt the nebula in just a few million years. Massive stars emit copious amounts of ultraviolet radiation, which ionizes the surrounding gas and heats it to tens of thousands of degrees, causing it to expand outward at high speeds. This creates an expanding bubble of hot, ionized gas that pushes into the cooler, neutral gas of the nebula, compressing it, and sometimes triggering new episodes of star formation at the edges of the bubble. Over time, the bubble can grow to tens of light years across, and if multiple massive stars form in the same region, their bubbles can merge, creating a superbubble that can disrupt the entire nebula. And when massive stars reach the end of their lives, just a few million years after they form, they explode as supernovae, releasing enormous amounts of energy and sending shock waves racing through the nebula at thousands of kilometers per second. These shock waves can compress the remaining gas and trigger one last burst of star formation. But they can also blow the gas away entirely, dispersing it back into the interstellar medium and leaving behind only the stars that have already formed. In this way, the lifetime of a nebula is intimately tied to the lifetimes of the stars it creates. And the most massive stars, which have the greatest impact on their surroundings, also have the shortest lives, which means that the nebulae that form them are among the most short-lived. But even after the nebula has been dispersed, its legacy remains in the form of the stars and planetary systems it created, and in the enriched gas that is returned to the interstellar medium, ready to become part of the next generation of nebulae and stars. And in some cases, the remnants of the nebula can persist as faint wisps of gas and dust, visible only in infrared or radio light, slowly mixing with the surrounding interstellar medium and fading into the background. And as you rest, you can let this be a soothing thought. Nothing in the universe lasts forever, not even the nebulae that give birth to stars. And yet the cycle continues, with new nebulae forming from the material dispersed by old ones, and new stars being born over and over again. For as long as the galaxy has gas to work with, let your breathing stay slow. And even as we drift into the final stretch of our journey through nebulae, where we can gather a few last thoughts about these cosmic clouds and the role they play in the universe. Nebulae are not just beautiful objects to observe. They are fundamental to the way the universe evolves, because they are the places where the raw material of the cosmos is transformed into the structures we see today: stars, planets, and potentially life itself. Every atom in your body was once part of a nebula, drifting through space, waiting to be gathered into a star, and then, billions of years later, incorporated into a planet, and eventually into a living organism. The carbon in your bones, the oxygen in your lungs, the iron in your blood, all of it was forged inside stars that formed from nebulae, lived their lives, and then returned that material to space, where it could become part of new nebulae and new stars. In this way, nebulae are not separate from us. They are part of our history, part of the long chain of events that led to the formation of the solar system and the Earth, and ultimately to life. And when we study nebulae, we are not just looking at distant clouds of gas. We are looking at the processes that shaped our own origins, the same processes that are still happening today in stellar nurseries across the galaxy. And in the future, long after the sun has died and the Earth is gone, the atoms that make up our world will be scattered back into space, perhaps to become part of a new nebula, where they will drift for millions of years before being gathered into a new star, continuing the cycle that has been ongoing since the first stars formed more than 13 billion years ago. It is a comforting thought, in a way, the idea that nothing is ever truly lost, that the material of the universe is endlessly recycled, and that every ending is also a beginning, a chance for something new to form from the remnants of what came before. And as you rest here in the quiet of your own room, you can let that thought be soothing. The universe is patient, and it has been creating and destroying and creating again for billions of years, and it will continue to do so for billions more. And you are part of that process, made of stardust, connected to the cosmos in ways that are profound and beautiful. Stay with that quiet feeling of connection and let your mind drift one last time through the nebulae we've explored together. We've seen Emission nebulae glowing red with ionized hydrogen, reflection nebulae shining blue with scattered starlight, and dark nebulae blocking the light from stars beyond. We've watched as gravity pulls gas and dust together, forming dense cores that collapse into protostars. And we've seen how those protostars grow into stars, clearing out the nebulae around them and leaving behind clusters of young, bright objects that will shine for millions or billions of years. We've explored the pillars of creation, towering columns of gas being eroded by starlight, and the Orion Nebula, a nearby stellar nursery filled with young stars and protoplanetary disks. We've learned how nebulae reveal themselves in different wavelengths of light, from the infrared glow of warm dust to the X-ray emission of hot gas, and how each wavelength adds a layer to our understanding. We've seen how star formation is driven by gravity, but shaped by pressure, magnetism, and radiation, and how the process is both rapid on cosmic terms and incredibly slow from a human perspective. And we've understood that nebulae are not permanent structures, but temporary phases in the life cycle of the galaxy, destined to be dispersed by the stars they create, only to reform later from the enriched material those stars return to space. All of these ideas are connected, woven together into a single story about how the universe creates. And as you drift toward sleep, you can let that story carry you, soft and gentle, like a lullaby sung by the cosmos itself. Let yourself sink even deeper now, into the final moments before sleep fully takes over. And as you do, remember that the nebulae we've explored tonight are still out there, drifting through the galaxy, quietly doing their work, forming stars that will shine for billions of years and planets that may one day host life. The universe does not need you to watch it or understand it for it to continue. It simply is patient and persistent, creating beauty in the dark, far from any observer. And that is one of the most restful truths of all. The cosmos is vast and indifferent, and yet it has produced you, a conscious being capable of wonder, capable of looking up at the night sky and asking questions about where you came from and what it all means. Nebulae are the answer to some of those questions, the places where stars and planets and people begin, the cosmic nurseries where everything we know and love was born. And as you rest here, breathing slowly, letting your thoughts dissolve into the darkness, you can take comfort in that knowledge. You are made of stars, shaped by the same forces that shape nebulae, connected to the universe in ways both physical and profound. And now, as this story comes to an end, you can let go completely, releasing the day, releasing the thoughts, and simply drifting like a particle of dust in a nebula, weightless and free, carried along by forces you don't need to understand, moving toward rest, toward peace, toward the deep, quiet darkness of sleep. Let your mind settle back into that quiet, comfortable rhythm, breathing slowly as we drift from the modern understanding of nebulae back to the nights when they were first being discovered. Imagine the night sky as it looked centuries ago, dark and pristine, without the glow of city lights, where early astronomers sat in the cold silence of their observatories, peering through long, brass telescopes, searching for comets. To these early stargazers, nebulae were often mysteries or even nuisances, faint, fuzzy patches of light that didn't move like comets, but hung suspended in the darkness, unchanging and ghostly. One of the most famous lists of these objects was created by Charles Messier in the 18th century, a comet hunter who kept finding these cloudy stars and noting their positions so he wouldn't mistake them for the comets he was actually looking for. It is a gentle irony that the list he made to avoid these objects became one of the most celebrated catalogs in astronomy, filled with the very nebulae we admire today: the Orion Nebula, the Eagle Nebula, the Crab Nebula, all recorded by a man who was simply trying to clear the way for his own search. You can imagine him sitting there, night after night, scratching notes onto parchment by candlelight, mapping the fuzzies of the sky with a patience that mirrors the slow drift of the nebulae themselves. And then came the Herschels, William and Caroline, a brother and sister team who swept the sky systematically, dividing the heavens into zones and exploring them strip by strip, like farmers plowing a field of stars. They found thousands of these nebulae, a word that simply means clouds in Latin, and they began to wonder what they truly were, whether they were clusters of stars so distant that their light blurred together, or if they were truly vast oceans of shining fluid. William Herschel once described a planetary nebula as looking like a star with a burr, a soft, imperfect point of light that defied the sharpness of the surrounding stars. As you rest, you can feel a connection to those quiet nights of discovery, the simple act of looking up and seeing something faint and beautiful, and not needing to know exactly what it is, but just appreciating its presence in the dark. The telescopes of that era were not powerful enough to reveal the intricate structures we see today: the pillars, the cavities, the shock waves. But they revealed something just as important: the vastness of the cosmos, filled with objects that were neither stars nor planets, but something else entirely. And as time went on, and our glass eyes grew larger and sharper, the fuzzies resolved into the magnificent clouds we know now. But the sense of mystery has never fully left them. Even now, when we look at a nebula through a small telescope, we see what Messier saw: a delicate smudge of gray light, a whisper of brightness against the black, requiring us to use our averted vision, looking slightly to the side to let the sensitive parts of our eyes catch the glow. It is a practice in softness, in not looking too hard, in letting the light come to you rather than chasing it. And that is a perfect way to think as you move towards sleep. You don't need to focus sharply. You can look with averted vision at your own thoughts, letting them be soft and fuzzy, drifting in the background while you stay centered in the quiet comfort of your bed. The history of astronomy is a history of patience, of waiting for clear skies, of waiting for light to travel across the universe, of waiting for understanding to dawn. And you can borrow that patience tonight. There is no rush to figure anything out. There is only the slow, steady sweep of the night, carrying you gently from one moment to the next. just as it carried the Herschels across the sky. Stay in this soft, historical drift. But let your imagination travel much farther now, stepping outside our own galaxy, the Milky Way, to visit our galactic neighbors dot in the southern skies, visible to the naked eye as detached pieces of the Milky Way, lie the Magellanic Clouds, two small satellite galaxies that orbit our own, trailing streams of gas like ribbons in the wind. Within the large Magellanic Cloud, roughly 160,000 light-years from Earth, lies one of the most spectacular nebulae in the entire local group of galaxies. The Tarantula Nebula dotted is a name that sounds frightening, but the nebula itself is a thing of immense, chaotic beauty. Also known by the catalog number 30, Doradus the Tarantula, is a giant star-forming region so massive and so luminous that if it were placed at the same distance as the Orion Nebula, just 1,300 light-years away, it would cast visible shadows on Earth at night and cover a patch of sky as large as 60 full moons. Imagine that for a moment, a glowing cloud so bright it acts like a second, pale sun in the night, washing the landscape in a soft, ghostly light. The Tarantula is the largest and most active stellar nursery in our galactic neighborhood, a place where the gas is churning with incredible energy, driven by the birth of supermassive stars. At its heart lies a cluster of stars called Roan 136, which contains some of the most massive stars ever discovered, titans that are dozens of times heavier than our sun and millions of times brighter. These stars are burning through their fuel at a furious rate, pouring out ultraviolet light that ionizes the surrounding gas and causes the entire nebula to glow with an intense, intricate brightness. The structure of the tarantula is complex, looking indeed like the legs of a giant spider, or perhaps more like the roots of a great cosmic tree, twisting and tangling through the void. But despite the violence of the star formation happening there, the distance makes it seem peaceful to us. A silent jewel in the southern sky, glowing steadily across the vast gulf between galaxies. And because the large Magellanic Cloud is chemically different from the Milky Way, with fewer heavy elements, the Tarantula Nebula gives us a glimpse into what star formation might have looked like in the early universe, when galaxies were younger and more primitive. It is a window into the past, a place where the conditions are raw and powerful. And yet, like all nebulae, it is also a place of creation, where the universe is building something new from the chaos. As you rest, you can picture this vast, glowing web of gas far away in another galaxy, silent and majestic, holding thousands of new stars in its tangled filaments. The light from the tarantula has traveled for 160,000 years to reach us, a journey that began long before recorded human history, crossing the empty darkness between galaxies to finally land on the retina of an observer or the sensor of a telescope. There is a comfort in that long journey, a reminder that light is patient, that it carries its message across the eons without fading, just as your own rest can be deep and enduring. Let the thought of that distant light soothe you. A soft beam traveling through the quiet dark, arriving gently, just as sleep arrives when you stop reaching for it, drift back now, closer to home, into the constellation Monoceros, the unicorn, where another beautiful shape waits in the darkness, soft and blooming. This is the Rosette Nebula, and its name tells you exactly what to imagine: a perfect cosmic rose unfolding in the depths of space, its petals made of glowing red hydrogen gas. The Rosette is a large emission nebula, roughly 5,000 light-years away, and like a flower, it has a center that seems to open up, revealing the heart within. But this center is not made of pollen. It is a hole, a cavity carved out by the stellar winds of a cluster of young, hot stars that formed right in the middle of the cloud. These stars, collectively known as NGC 2244, have cleared the gas away from their immediate vicinity, creating a dark, circular void surrounded by the glowing red walls of the nebula. As the radiation from the stars hits the surrounding walls, it causes the gas to glow, creating the appearance of petals catching the light, with dark lanes of dust threading through them like the veins of a flower. Looking at the rosette, it is easy to forget the immense scale. The flower is over 100 light-years across, a bloom so large that light takes a century to cross from one petal to the other. And within the petals, looking closely, astronomers have found tiny dark specks, known as globules, which are dense knots of gas and dust that are resisting the erosion of the stellar winds. These globules are like seeds, protecting the potential for future stars inside them, holding firm against the stream of radiation that is sweeping the rest of the gas away. It is a beautiful image to hold as you relax, a rose in the dark, blooming in slow motion over millions of years, opening its center to the light while holding seeds of new life in its petals. The red glow of the rosette is soft and warm, the color of hydrogen alpha emission, a specific wavelength of light that is soothing to the eye and to the mind. Imagine yourself floating near this cosmic flower, watching it drift in the silence, its shape perfect and still, preserved by the vastness of space. There is no wind to shake these petals, no wilting, only the slow, graceful expansion of gas and light, a blooming that lasts for eons. The universe is full of these accidental beauties, patterns that emerge from the laws of physics that just happen to look like things we know and love: a rose, a spider, an eagle, a horse's head. It is as if the sky is a great canvas where our imagination can find familiar shapes in the clouds, comforting us with the recognition that we are part of the same nature that shapes the stars. Let the rosette be your visual anchor for a few moments, a red flower in the black velvet of night, soft, open, and peaceful. Let your breathing deepen, becoming slower and more rhythmic as we turn our attention to one of the most delicate and ethereal sights in the sky, the Veil Nebula. Unlike the heavy, churning clouds of star formation we have talked about, the Veil is a supernova remnant, the ghost of a star that died thousands of years ago. It is located in the constellation Cygnus, the Swan, and it looks like a tangle of finest silk thread spun across the stars in a great looping circle. The Veil is what remains of a shock wave. When the star exploded, it sent a blast wave racing outward, and as that wave collided with the sparse gas of the interstellar medium, it heated it up, causing it to glow in thin, wispy sheets. These sheets are incredibly thin, almost two-dimensional from our perspective, and we see them edge on, which makes them look like filaments of rope or twisted wire. One part of the nebula is called the witch's broom, a long, narrow streak of glowing gas that looks like a bundle of straw swept across the sky. Another part is called Pickering's triangle, a faint, triangular wisp of light that looks like a piece of gauze floating in the wind. The colors of the veil are exquisite. Oxygen glows in a soft, teal blue, while hydrogen adds traces of deep red, and the two mix together to create shades of violet and pink. Looking at the Veil Nebula is like looking at lace or smoke that has been frozen in the quiet air of a room, preserving every curl and eddy dot. It is hard to believe that such a delicate structure came from such a violent event. But that is the way of the universe. The energy of destruction is transformed into the beauty of the remnant, and over time, the violence fades, leaving only the art. The veil is expanding, but so slowly from our distance that it appears motionless, a static sculpture of light that has hung in the sky for millennia. You can imagine the silence of it. No sound of explosion, no roar of the shock wave, just the quiet glow of ionized gas in the vacuum. The filaments are so fine that they seem to dissolve into the background stars, blurring the line between the nebula and the empty space around it. As you rest, let your own thoughts become like the veil, thin, wispy, transparent, untangling themselves from the knots of the day and floating free. You don't need to hold a solid shape right now. You can be diffuse, spread out, permeable, letting the peace of the night pass right through you. The Veil Nebula reminds us that even after the end of a star, there is beauty, and that what is left behind can be just as wondrous as what was there before. It is a ghost, yes, but a friendly one, a light in the window of the galaxy, watching over the quiet dark. Keep drifting, soft and weightless, as we move from the delicate threads of the veil to the geometric perfection of the planetary nebulae. We mentioned these earlier, the glowing shells expelled by dying sun-like stars. But some of them deserve a closer look because of their symmetry, which feels almost constructed, like a cosmic diagram. Consider the Helix Nebula, often called the Eye of God or the Eye of Sauron by those with a more dramatic flair, though tonight we will stick to the gentle image of an eye watching the cosmos. It is one of the closest planetary nebulae to Earth, located in the constellation Aquarius, and it looks like a giant golden eye with a blue pupil. The pupil is the hot white dwarf star remaining at the center, and the iris is a disk of glowing gas that surrounds it, red on the outside and blue on the inside. But the helix is not actually a flat ring. It is a long tube of gas pointing almost directly at us. So we are looking down the barrel of the cylinder, seeing the glowing walls stacked on top of each other to create the illusion of a ring around the inner edge of the ring. The Hubble Space Telescope has revealed thousands of cometary knots, dense blobs of gas with glowing tails pointing away from the central star. These knots are fascinating. They are about the size of our solar system, and they may be formed from the collision of the dying star's winds with existing material. Possibly even the comets that orbited the star when it was alive. Imagine that thousands of comet-like worlds, surviving the death of their sun, now glowing in the shell of the nebula, swimming upstream against the stellar wind. Then there is the ring nebula in Lyra, the classic smoke ring of the summer sky dot. It looks small and distinct through a telescope, a perfect little Cheerio of light, grayish-white to the eye, but revealing brilliant blue and orange in photographs. The Ring Nebula is a textbook example of a star gently puffing off its outer layers, expanding into space like a slow-motion breath that never ends. These shapes, rings, cylinders, hourglasses, are the geometry of gravity and rotation. Simple laws creating perfect forms in the vacuum. There is something soothing about symmetry, about the way the universe naturally seeks balance and order, even in its expansions. As you lie there, you can feel the symmetry of your own body, the balance of your breath, the steady rhythm of your heart mirroring the quiet order of the nebulae. You are a structure in space, too, held together by forces, warm and alive, resting in your own orbit of sleep. Let the image of the helix, that great, calm eye, watch over you, not with judgment, but with a wide, unblinking peace, seeing everything and disturbing nothing. Let's drift now into a different sense, one we rarely associate with astronomy, the sense of smell, or rather, the chemistry of the clouds. We often think of space as a sterile vacuum, but nebulae are chemically rich environments, filled with molecules that would be familiar to us here on Earth, and some that are strange and exotic. If you could travel to the center of the galaxy, near the giant molecular cloud Sagittarius Beidou, and sample the molecules drifting there, you might be surprised by the chemistry. Astronomers have detected ethyl formate in these clouds, the chemical that gives raspberries their flavor, and rum its smell. It is a whimsical thought to hold as you drift toward sleep. That deep space might smell faintly of raspberries and rum, a sweet, fruity cocktail drifting between the stars. Of course, there are other, simpler molecules too, plenty of water, not as liquid, but as ice frozen onto the surface of tiny dust grains. In the cold, dark hearts of molecular clouds, water is everywhere, coating the dust like frost on a window pane in winter. There is also ammonia, methane, and carbon dioxide, the simple ices that make up comets. But more complex things are forming too. Astronomers have found polycyclic aromatic hydrocarbons, or PAHs, which are the same molecules found in the charred crust of toast or the smoke from a candle. So perhaps space also smells a bit like a campfire that has just burned down, a smoky, woody scent lingering in the cold air. And recently, they have found even larger molecules, huge carbon chains and rings that are the precursors to the building blocks of life. These molecules form in the quiet, cold protection of the dark nebulae, where the dust shields them from the destroying ultraviolet light of stars. Within these dark clouds, chemistry is happening slowly, atom by atom, creating complexity out of simplicity, preparing the ingredients that might one day land on a young planet and start the long chain of evolution. It turns the nebula into a kitchen, a laboratory, a garden where the seeds of life are preserved in deep freeze. You can imagine the air in your room as being connected to this cosmic chemistry, Because the oxygen you breathe and the carbon in your cells came from sources like these. The universe is not out there, separate from you. It is a continuum of matter and energy. And the sweet smell of a raspberry or the scent of rain is just the local expression of a chemistry that spans the galaxy. Let this thought ground you. You are at home in the universe, made of the same stuff, breathing the same elements, resting in the same vast chemical sea. Now shrink your focus down, smaller and smaller, until you are no longer looking at the giant cloud, but at a single, tiny grain of dust drifting within it. This dust grain is microscopic, smaller than a particle of smoke, a tiny speck of silicate or carbon formed in the cooling wind of an old star. Imagine its journey, which is a story of incredible patience. It begins its life being blown out of a red giant star, tumbling into the vast emptiness of the interstellar medium for millions of years. It drifts alone, pushed gently by the light of distant stars, cooling down until it is almost as cold as space itself as it drifts into a dense molecular cloud. Atoms of hydrogen and oxygen bump into it and stick, freezing instantly to form a layer of ice. Over time, the grain gathers a thick coat of ice, becoming a tiny, frozen pearl, carrying water and organic molecules on its back. It might drift like this for eons, a silent traveler in the dark, until gravity finally begins to pull it toward a new center of activity. It falls inward, joining trillions of other grains, swirling into a disk around a newborn protostar. Here, the journey speeds up. The grain collides with others, sticking together, growing from a microscopic speck to a pebble, then a rock, then a boulder. It might become part of a comet, destined to orbit the star in long, lonely loops, preserving its icy coat forever. Or it might fall closer to the star, where the heat melts its ice, and it becomes part of a rocky planet like Earth, locked deep in the mantle, or resting on the surface as a grain of sand on a beach. Think of how many journeys are hidden in the sand of a beach, how many stars and nebulae are represented in a handful of grit. The dust grain doesn't know where it is going. It simply yields to the forces around it, drifting when the space is wide, sticking when the crowd is dense, resting when it lands. You can be like that dust grain tonight. You don't need to direct your course. You can just yield to the gravity of sleep, letting yourself be pulled slowly inward, drifting through the dark, gathering rest like layers of soft ice. There is no effort in drifting, no work in falling. It is the most natural thing in the world to let go and let the universe carry you. As we near the end of our journey, let's zoom back out one last time to look at the weather of the galaxy itself. We tend to think of space as empty, but astronomers call the stuff between the stars the interstellar medium, or ism, and it has phases. Just like water has phases of ice, liquid, and steam, there is the hot ionized medium. Gas heated to millions of degrees by supernovae, tenuous and spread out, blowing like a hot wind through the galaxy. There is the warm, neutral medium, the gentle background gas that fills the spaces between the arms. And there are the cold molecular clouds, the dense, dark nebulae we have been talking about, which are like storm clouds gathering in the galactic atmosphere. Matter is constantly cycling between these phases, evaporating from clouds into hot gas, and condensing from hot gas back into clouds, driven by the rotation of the galaxy. Imagine the Milky Way breathing, a slow respiration that takes hundreds of millions of years. As the spiral arms sweep through space, they compress the gas, triggering the formation of clouds and stars, the inhalation of the galaxy. And as the massive stars explode and the winds blow, the gas is dispersed and heated, the exhalation dot. It is a rhythm so slow it looks like stillness to us, but it is there, a heartbeat of creation and destruction that sustains the galaxy. You are resting inside this breathing creature, a tiny, protected part of the great galactic organism. The weather out there is calm right now. In our little corner of the Orion Arm, we are in a quiet, bubbly space, protected from the fiercest winds, drifting in a calm eddy of the interstellar rivulet. That sense of protection settle over you, the walls of your room, the roof over your head, the blanket over your body. These are your personal nebula, your shield against the cold and the dark within this shelter. The conditions are perfect for rest, for the slow recharging of your energy, just as the cold clouds are perfect for the formation of stars. You are in your own quiet phase, safe, gathered, and still. And so, we come to the end of our drift through the nebulae, having traveled from the birth of stars to the death of suns, from the vast spiderweb of the tarantula to the microscopic journey of a dust grain. If you are still awake, you can let these last words be a final, gentle invitation to let go completely. The universe we have explored tonight is a place of immense time and patience, where nothing happens in a hurry and where even the most dramatic changes are softened by the vastness of space. You have seen that the dark is not empty. It is full of potential, full of the raw material for new light. Your sleep is like that dark nebula, a quiet, necessary time where your body and mind can gather themselves, repairing and renewing, preparing for the new day that will eventually dawn. But that dawn is far away. Right now, there is only the night, the steady, comforting dark that holds you. Let the stars blur into soft points of light. Let the nebulae fade into the background, just gentle clouds of color behind your closed eyelids. You are safe here, anchored by gravity, held by the bed, watched over by the ceiling, drifting in the quiet current of time. The rotation of the earth is carrying you away from the sun, deep into the shadow, and you can ride that shadow all the way down to sleep. Thanks for drifting through the cosmos with me tonight. If this journey helped you relax, you're welcome to like and subscribe so you can return for more quiet science stories. Until next time, let your breath stay slow. Let your thoughts fade gently into the dark and rest beneath the wide, patient sky where nebulae are still glowing softly, still forming stars, still doing the slow, beautiful work of creation. Good night.